All right, guys. Today we are going to talk about energy charts. So when I'm talking about energy charts, I'm talking about how can we give ourselves a visual for what energy is happening at different times. This is kind of like when we did force diagrams, how it's a super useful tool to help us really wrap our heads around problems. So kind of going into a review of a couple different terms. Now, the term kinetic energy, you might see this labeled a lot of different ways. You might see the K, you might see K, you might see KE or EK. Typically, I'm going to use the term K. This is energy stored within the motion of an object. Now we have gravitational potential energy. UG is what you're going to see typically on the AP sheet, but you also, if you're looking at different resources, might see PEG for potential energy gravitational, or just EG for energy gravitational. Elastic or spring potential energy, this energy stored within a spring. Remember, this has to be a stretch or a compress. So just going to put that there. You might see PE, SP, PEEL, EEL, or for us, we're going to see US if you're looking like official AP materials. And then another thing is the dissipated energy. So this is one I did not talk about. This is going to be that thermal energy. So typically we're going to say KTH, but you also might see ETH, you might see work non-conservative, or you might just see work. And side note, we haven't gotten into this yet, but work is just the change in energy. So if energy is leaving or entering our system, we're just calling that work. So this dissipated energy typically is going to be through temperature, light, sound, anything along those lines. Now, a non-conservative force can cause a change to mechanical energy. That's mostly when we're including friction. Conservative forces, those are going to turn into other forms of mechanical energy. And now this is where I'm going to contradict everything I said in the last video. When you see the term mechanical energy, it just says mechanical without the kinetic by itself. This is the sum of all the energy. So mechanical energy, that's different than the KEM or the KM that we talked about last time. That KM is the kinetic energy up top. So a couple terms, just to review, making sure we're all using the same language. All right, so we're going to actually talk about pie charts. Pie charts is the first way for we're going to identify what energy is in our system, what's happening to our energy, where it's going. So the size of the pie represents the total energy in the system. So if you've got a bigger pie, you have more energy, versus if you have a personal size pie, you have less energy. The amount of energy won't change. So the pie size won't change throughout the system. You only have so much energy in your entire system. If you have a different system, it might have different size pies. And this is easiest in a closed system. So a closed system means that the energy is not entering or leaving, the total amount of energy stays the same. I like to think of this in the context of money. So I have a certain amount of money. My money is located in different locations, but the amount of money I have doesn't change because I'm not spending any of my money. So I might have some money in my wallet. I might have some money in like a top drawer hidden somewhere. I might have some money in my savings account. But overall, my amount of money isn't changing because I'm not spending my amount of money. It's just located in different locations. Same thing would happen with energy. We might have some kinetic energy, we might have some gravitational energy, and we might have some elastic, or remember, we could call this spring energy. You're going to see those terms interchanged. But the total amount of energy is going to stay the same. Now, I might be able to move it from my wallet to my top drawer, from my wallet to my savings account, but I'm not spending any of my energy. So when we go to create a pie chart, what we're going to do is we're going to ID the system with a dotted line and a zero reference line. So the cool thing about energy and physics in general is I get to decide where zero is. I get to decide where is my thing I care about. So in this situation, most of the time, I'm going to make the ground zero. It just makes sense. And my system is my object, and we're going to say the earth. So I might actually draw a around my entire thing, around the earth too. If we want to include gravitational energy, you have to include the earth because the earth is what causes gravity. If you don't want gravitational energy, don't include the earth. So our example here says, a ball is held above the ground and it's dropped so it falls straight down. So what energies are changing? At the top, I'm going to think to myself, okay, I've got some gravitational energy up here at the top because it has height. But by the time I reach the bottom, all that gravitational energy is going to turn to kinetic energy. And when I say the bottom, I mean the moment right before it hits the ground, just like when we were talking about kinematics. Now here, I'm not quite halfway down. I'm about a third of the way down. So in the middle, I'm going to have gravitational energy and kinetic energy. So to chart this, what I'm going to do, at the beginning, I have all gravitational energy. So my entire pie is gravitational. About a third of the way down, because I'm not halfway yet, I'm going to say a third. That's a terrible third, but it'll do. I've switched to a third of the kinetic energy, but the gravitational energy has gone to 2/3 because it's 2/3 of it still has 2/3 the height it originally had. And then at the bottom, where all the kinetic energy. So you can see that as the time is going, as my ball is falling, I can see the shift of what's happening to the kinetic energy and the gravitational energy of my object. Let's look at another example. So another example would be a jumper on a trampoline. You can see I've already drawn my zero reference line. It's the ground, the bottom of the trampoline. I've got my jumper and the whole thing is in my system. So at the beginning, I am looking, I've got a little bit of height, so I know I'm going to have some gravitational energy. And I'm not moving, so there's no kinetic, but I've got some spring energy as well. Now, I don't have a lot of height, so I'm going to say it's mostly spring energy here. And the amounts don't really matter that much. I'm actually, yeah, we'll go with that. The amounts don't totally matter because we don't have numerical values yet. The only thing that matters is when you're halfway up in the air, you have half that gravitational energy. But here, I've got some gravitational and we've got some spring energy. So I'm just showing we've got gravitational and we've got spring. My next location, my person has height still. They're above this zero reference line, so we've got some gravitational energy. But now they're moving, and I've got some kinetic energy. This is the fastest they're going to be moving. Now, the trampoline is no longer compressed, so there's not going to be any spring energy anymore. And since I have more height, I have to show that gravitational increasing because they went up. So I'm going to have a little more gravitational, and whatever's left over is going to be my kinetic energy. Now, as my person moves up, I'm still moving because we have an arrow to represent motion, and I still have gravitational energy. But as I'm moving up, my gravitational is going to increase and that kinetic is going to decrease because my object's slowing down. The slower it's moving, the less kinetic energy it's going to have. So I might I'm going to show that the gravitational is increasing, more and more gravitational energy, but that kinetic energy decreased, so it's going to be smaller. Now, when I'm at the top, there's no more arrow. This represents that it's staying still. So we just have gravitational energy. The spring isn't stretched or compressed anymore, so there's no elastic energy. So at the top, my jumper just has gravitational energy. So ideally, what I'm able to see through this time, I'm able to see that the spring energy is changing to gravitational energy, and then there's kinetic energy in the middle there. But the total amount of energy has not changed. Now, there's another type of graph we can look at called a bar graph, or we call LOL graphs. They're called LOL graphs because if I were to draw axes, I have L, and then we have a system in here, and then we have an L. That's why they're called LOL. So for this shows work as a transfer of energy. These are both best used when you have an open system. Open systems mean energy can come in and out. Just like if you have an open door, things can go in and out, versus if you have a closed door, things have to stay in. So in this, we're always going to be given an initial state and a final state. That's going to be the initial is going to go on the left side, the final is going to go on the right side. Now, the total number of boxes have to be consistent throughout, but I'm going to show you what I mean by the ins have to be the same as the outs. Your inputs and outputs have to be the same, but they don't have to stay in the system. So in this situation, we've got a ball is dropped from a certain height just before it starts moving, and the final state's the spring's fully compressed. So in this box here, this is what we draw with our systems. We put our ball is in our system, our spring is in our system, and the earth is in our system. So at the beginning, when my ball has some height, I have all gravitational energy. You'll see down here, this is an example where our system, like our type changed, like the lettering, that's okay. And I'm going to say there's 4 boxes of gravitational energy. So I'm going to say All of my energy is gravitational energy because my ball is not moving. It's up in the air. It has some height, but the spring isn't compressed yet. My zero, again, you can decide your zero reference line. I'm going to make my zero line down here. And after, for my final state, the spring is fully compressed, but the ball's not moving anymore. Now, there still is some height, so I know I still have a little bit of gravitational energy. Not much, but some. And the rest of that energy has turned into spring or elastic energy. Now, since I had 4 boxes at the beginning and no energy entered or left the system, we're going to have 3 boxes here because I want the total to stay 4, 1, 2, 3, 4. You could have made this 3 and 2, whatever numbers you were making it, as long as you had 4 before, 4 after, or 5 before, 5 after, as long as you're consistent. Now, the question is, what happens when we change our system? What happens when I change what I'm looking at? So we're going to say the ball and the earth are in the system, but we're going to pretend like we can't see the spring. It's almost as if this doesn't exist. So at the beginning, our ball and earth are in the system, so we still are going to have those 4 boxes of gravitational energy. And then it's almost as if we see the ball fall and it just stops. We don't know what stops it. We can't see what stops it. There's just a mystery box there that stopped our object. So at the end, we still see it's above the ground, but we don't know where that energy went. There are 3 boxes of energy unaccounted for because we had 4, now we have 1. So 3 disappeared. So I'm going to draw 3 leaving the system, and we know they left the system to the springs. We actually know what happened, but the energy's gone. This is what's called when work is done on the system. Energy entering or leaving our system is called work. So energy comes out. We still have 4, and then we have 1, 2, 3, 4. If I wanted to write an equation for this, I would write an equation that said gravitational energy minus work, because there's that work and it's leaving, so it's a minus, equals our gravitational energy. And I might say initial and final here. So we can start to put some equations to this to really make sure we can practice around what's going on. Maybe for the first one, we would have said gravitational energy equals gravitational energy plus spring energy. And this would be I, and this would be F for initial and final. So we can start to, even though we don't have numerical values, we don't know like the true equations for these types of energy yet, we can start to put numbers to this and like quantitative values. I've got one more example for us. What if we just had the spring in the system? So only the spring existed, just the spring. It was almost as if we don't see this ball here, we don't see this ball here. We just see a spring, and then suddenly the spring is smashed. At the beginning, the spring is not compressed, it's not stretched, so we have no energy at the beginning. And then suddenly it's as if magic happened and it were smashed. We don't know what smashed it. We can't see it. Now, I know the ball did it, but what we would do here is we would see that 3 blocks of energy just entered our system. Now, this is from the ball. We know it's from the ball, but there's just 3 energies coming in. If we were to write an equation for this, we'd say 0 plus work, because there's 0 energy here, plus the work from the ball, is going to be equal to our, I'm just going to use this notation, elastic. Or we would say work equals US. I'm sorry, I switched the notation here. This is the one AP wants us to use. So overall, these are really challenging. We're going to do some practice with them. I highly, highly, highly encourage you to do the practice sheets that are in the should do folder for this, because this is probably the hardest thing that we've seen in a while. So let me know if you have questions, and I'm here to help.